Every reactor, every jet engine shaft, every deep-sea platform on Earth traces back to a handful of forging presses. Some weigh 60,000 tons. Some hit accurate to 1/100th of a millimeter. Only a small number of specialized forging plants worldwide can build the biggest parts humanity needs. What actually happens inside? Stay tuned. The whole supply chain rests on it. "17,000 tons of squeezing force lands on one glowing block of steel, and the machine holding that force doesn't even blink. Building the press itself took a full industrial site, poured foundations, precision-machined columns, and cranes big enough to lift the parts other cranes install. The press is the product before the product. Watch a 13,000-ton press slowly kiss a red-hot billet. A 450-ton manipulator swings the workpiece around like it weighs nothing. Laser lines mark the strike zone. There is no such thing as close enough at this scale. How does a machine push this hard without cracking its own bones on the very first stroke? The answer starts on a factory floor that looks less like a workshop and more like a stadium under construction. A 10,000-ton forging press doesn't arrive in a crate. It shows up in pieces that a mobile crane has to lift one at a time. Then another crane holds while workers on scissor lifts thread pins the diameter of a dinner plate. Base columns go in first, standing like the legs of something that shouldn't exist. Then come the tie rods, the crossheads, the massive upper plate. Final assembly took 3 months, and that was after the parts were already made. Anyone here from a heavy manufacturing region? Ohio, Pennsylvania, the Ruhr Valley, Nagoya? How does your local plant handle final press erection? Comment where you're watching from. Every alignment has to hold for decades of pounding. Off by a millimeter and the whole frame walks under load. Before a bolt goes in, engineers build the whole thing twice. Once inside a computer, once for real. The digital assembly runs first because the physical version can't be undone. Cylinders, valve manifolds, gear housings, ram guides, every internal oil path and every mating surface gets simulated under full load. Only then does the foundry pour anything. Individual castings arrive at the shop, weighing more than most freight locomotives, and each one has to slide into position without touching anything else on the way in. Cranes hand off to cranes. A sub-assembly on the shop floor already looks like a finished machine, except it's just the frame. Control cabinets show up dead last. Bolt a house together and the walls hold each other up. But bolt this thing together and every wall is trying to pry itself loose the second you plug in power. Push those numbers further. 540 meganewtons, roughly 60,000 tons of press force. And now you know why the pit is dug 24 meters deep before assembly even starts. The castings come from 4 countries, 34 parts, each between 100 and 310 tons. The 4 conical guides are among the largest castings possible on Earth, and they cross oceans before ever meeting the press. Tie rods over 25 meters long, roughly 1 meter thick, forged on another giant press somewhere else in the world. Then the lower crosshead, 1,200 tons across 4 pieces, gets lifted by a mobile tower and lowered accurate to 1/100th of a millimeter. Hold on, 1/100th of a millimeter on 1,200 tons? That is the actual tolerance. The press can't be commissioned if the geometry drifts. Smaller presses tell the same tough story with less weight. The design still has to withstand its own forces. A 4,000-ton hydraulic forging press uses what engineers call a pull-down, 2-column layout. Instead of pushing the ram down from above, the cylinders pull the ram down from below through the columns. That inverted arrangement keeps the loaded section short, cuts frame flex, and lets the press hit its target dimension within 1 millimeter across the workpiece. Every stroke is a controlled release of stored hydraulic energy. The operator sits behind glass a few meters away, running the whole thing with a joystick and a keyboard. Around the machine, the hydraulic power unit takes up its own room. Pumps, filters, accumulators, electrical cabinets, cooling loops. The press you see doing the work is maybe a third of what actually makes it work. Rest of it hides in the basement, quietly earning its paycheck. All that structure exists for one reason: to hold up the second force arrives. Inside a working forging plant, the presses share the floor with ring rollers, hammer lines, robotic transfer arms, induction furnaces. Glowing billets move between stations on rails and manipulators. Dies come down, steel deforms, cycle resets. Everything on the floor was engineered around one shared assumption: the ground will shake, and the ground had better not move. But building the frame is only the surface layer. Where does the actual force come from? And how does the machine generate 17,000 tons without turning into an explosion? The force isn't stored in the frame. It's stored in oil. A forging press turns pressurized hydraulic oil into linear push-through cylinders, and the cylinders themselves are engineering pieces most folks never think about. At one Norwegian shop that's been building these since 1936, piston diameters run from 20 millimeters to 2,000 millimeters, with stroke lengths up to 20 meters. Submerged arc welding joins the tube sections. Every cylinder gets pressure tested, function tested, particle counted for oil cleanliness. A cylinder that leaks in a normal machine is a nuisance. A cylinder that leaks in a 17,000-ton press is a demolition permit. Raw force is useless without something telling the oil where to go, when to go, and how fast. That's the job of the valve blocks. Manifolds that route high-pressure oil into and out of every cylinder in the machine. At one manifold shop, 4 CNC machining centers work as a linked, flexible system with over 1,000 tools between them, because each block needs dozens of internal cavities drilled at precise angles. Then comes thermal deburring. The part gets sealed inside a chamber. A mix of methane and oxygen fires off, and the resulting flash at over 1,300 degrees Celsius vaporizes every microshaving still stuck inside the drilled holes. One loose chip inside a valve block will jam a cylinder mid-stroke, which, on a forging press, means the whole shop stops until somebody with a wrench the size of a golf bag shows up in a bad mood. Spools get ground after hardening because the tolerances are so tight the raw machined finish isn't good enough. Every manifold is function tested and pressure tested before it leaves. This shop alone puts out more than 15,000 hydraulic valve blocks per year for machines around the world. Shrink the whole idea down, and this is what the system looks like. A 40-ton self-contained axis packs a servo-driven pump, cylinder, control block, and touchscreen into one unit. Pump pushes oil, cylinder moves, sensor reads position, controller adjusts. Now imagine the same architecture, but the cylinder is roughly the size of a shipping container. Then the end fittings go on by hand. Rod ends, clevis mounts, threaded caps. Someone in gloves aligns, threads, and torques every one. On a small cylinder, it takes minutes. On a press cylinder, the same joint gets torqued with a wrench the size of a workbench and checked twice. Every finished cylinder gets a full workover. CNC turning cuts the rod and bore, seals go in by hand, the assembled unit gets sprayed and hung to cure, then labeled and tested. Same sequence at every scale. The tolerances just get meaner as the parts get bigger. All that hydraulic force still has to get transmitted somewhere, through gears, shafts, and drive units that carry the same punishing loads. In steelmaking and rolling plants, drive gears with modules up to 40 and diameters up to 6 meters are welded, milled, case-hardened, and ground under constant inspection. A double helical spur gear at 4.5 meters across weighs around 45 tons on its own. Ultrasonic testing checks the teeth after hardening. Grinding fine-tunes the tooth flanks. The gear housings are made in the same shop. Then the whole unit is pre-assembled, and the contact pattern between the gears is dialed in using eccentric sleeves. Years later, if the foundation settles even slightly, those same eccentrics let a technician realign the gears without pulling the housing apart. That's the small detail separating industrial machinery from the disposable kind. You can actually fix it. Try that with a smartphone. Modernization jobs on this scale mean replacing a full drivetrain on a running plant in days. Foundation blocks with new gearboxes and motors get assembled off-site, tested, then swapped in during a scheduled shutdown. But even the meanest press is useless if nothing can put the workpiece under it. So what actually moves 300 tons of glowing steel into position? Safely, precisely, and without putting the operator in danger? Here's the piece nobody thinks about until they see it move. A rail-bound forging manipulator carrying a glowing gear blank straight toward a press that could flatten a pickup truck without noticing. These machines run on tracks, grip the workpiece with hydraulic tongs, and position hundreds of tons within a few millimeters. Newer drive systems cut cycle time by up to 30%, meaning the steel spends less time cooling between strikes. Shrink the same idea down, and you get the workhorse of most open-die forging shops. A 20-ton hydraulic manipulator on tracks pairs with a mid-size forging press to handle aviation-grade workpieces, the kind of parts that end up inside jet engines and landing gear. If you've spent time on an open-die floor, tell me below what the manipulator operator gets wrong most often. The manipulator's tongs pinch, rotate, tilt, and slide the workpiece through every stroke. Coordination between press operator and manipulator operator has to be tight enough that neither has to shout. Miscommunication doesn't just ruin the part, it can bend the tooling. The real limit in open die forging usually isn't the press, it's the temperature of the workpiece and the speed of the handoff. Every second the steel sits outside the furnace, it cools, and every degree it loses makes it harder to shape. Before any manipulator can pick up a workpiece, the workpiece has to exist. For the biggest forgings, that means a multi-ladle pour, several ladles of molten steel emptied at once into one mold. Hundreds of tons of steel poured in seconds. Not a lot of room for someone to sneeze at the wrong time. Now put all three together on a working shop floor. Furnace on one side, press in the middle, manipulator running between them. A glowing billet gets pulled out, swung over, dropped into the die. Ram comes down, steel elongates and reshapes under stroke after stroke. Manipulator rotates the workpiece a quarter turn, ram again, another quarter turn, ram again. The finished piece, still red hot, gets lifted by an overhead crane and carried off to cool. Cycle time depends on furnace throughput as much as press throughput. Half of what makes a shop productive is the timing between machines, not the machines themselves. The other half is not dropping anything. Watch it sped up, and the pattern gets obvious. A 150-ton disc gets consolidated on a 10,000-ton press through dozens of strokes. Between each strike, the workpiece rotates a few degrees. The press barely seems to move. On a fully automated forging line, the timing gets even tighter. A 6,300-ton press sits at the center, but around it there's a full production line. Induction furnace feeding billets, transfer arms moving them to the die, a conveyor moving finished parts to a bin, robotic grippers handling swaps between stations. The yellow flywheels on the side of the press store rotational energy between strokes, so the machine doesn't have to draw peak power from the grid every time it strikes. Every stroke shapes a part in seconds. Between strikes, a new billet is already inbound. The whole line runs on one simple principle. Nobody should ever be near a hot workpiece if a machine can do the reaching instead. One mistimed transfer means either a jammed workpiece stuck between the dies or a hot billet on the floor. Neither ends the shift with a party. The real limit on lines like this is furnace capacity.
The press could hit faster if the steel got hot faster. But even the meanest coordinated line runs into one hard wall. The machine itself is made of metal, and metal doesn't enjoy hitting itself millions of times without complaining. So how do you actually build the parts going inside a machine this big? Making the parts starts with the oldest trick in the shop, open die free forging, where the metal has nowhere to hide. A glowing bar sits on the anvil, ram comes down, manipulator gives it a quarter turn, ram again. Simple in concept, thoroughly humbling in practice.
Free forging is where you go when the part is so big or so critical that a die can't survive making it. The ingot starts life in an electric arc furnace, holding up to 50 tons of liquid steel per heat. After ladle refining and vacuum degassing, it gets cast. The largest ingot runs 76 tons, poured from 2 heats combined. A 76-ton ingot is basically a small building tipped on its side, and they cast it in one go. Then it goes into the annealing furnace, up to 1,200 degrees Celsius, and lands on a 60 meganewton press. The manipulator grips the forged end, and the pre-forging plus upsetting cycle begins. Turbine shafts and turbine wheels take shape stroke by stroke. The real limit on the whole line is furnace throughput. The press can strike faster than the steel can reheat, so productivity comes down to how fast the surrounding equipment can keep up. You've got the world's meanest hammer waiting on a very slow toaster. Not every forging is a giant shaft. A huge chunk of forged output ends up as plain-looking steel bars for tool steels and heavy machinery. For these, square or rectangular ingots make more sense than round ones because they nest cleaner into the die. Same electric arc furnace, same ladle furnace and vacuum degassing, same optional electroslag remelting when the customer needs extreme purity. The ingot leaves the pouring pit at around 700 degrees Celsius, still red inside, then gets bumped to 1,200 degrees in the annealing furnace before hitting the 60 meganewton press. Top and bottom get flame cut off because those ends contain the impurities that floated up during solidification. After heat treatment, hardness is checked electronically, ultrasonic testing scans the interior for defects, and the bars get marked and shipped. The whole point of forging a bar instead of casting it is closing the internal voids the casting process leaves behind. Casting gets you the shape. Forging gets you the trust. Now flip the whole idea around. Closed die forging, where the shape lives inside the tooling and the steel just has to fill it. Instead of an open anvil, the workpiece drops between 2 die halves carved into the exact geometry of the final part. Ram comes down, the metal squeezes into every corner of the cavity. Flanges, gears, crankshafts, valve bodies. Anything produced in volume ends up here. Try pressing cookie dough into a pan and you get the idea. Except the pan is steel, the dough is 1,200 degrees, and the rolling pin weighs 3 tons. Closed die gives you repeatability. Free forging can't touch. Then there's the version that skips heat entirely. A cold press brake bending thick plate under 6,000 tons of force. At 6,800 millimeters long, this is one of the largest press brakes ever built. Cold bending doesn't have the flow control of forging, but for heavy plate destined for structural work, it's the fastest way to put a controlled bend into steel that thick. Moving the machine to the customer alone required a multi-axle transporter and a crane rated for the heaviest lifts. So all these forming methods exist. But why bother forging on such wild scales? What actually needs a part that only a few plants on Earth can make? The answer sits inside every serious power plant, every reactor pressure vessel, every deep-sea platform. Small modular reactor components start as glowing forged blocks the size of small cars, hoisted between furnace and press by overhead cranes. The tolerance stack on a reactor forging isn't demanding. It's the line between certification and rejection. The reactor pressure vessel is the piece that shows why giant forgings still exist as a category. It is also one of the few components in a nuclear power plant that simply cannot be replaced once the reactor enters service. For AVVER 1200 reactor, the vessel is built from a stack of forged shell rings: vessel flange, nozzle shell rings, support shell ring, central shell ring, lower shell ring, plus a hemispherical bottom head. The bottom head alone is formed from an ingot weighing up to 360 tons. Every shell ring is forged, machined, ultrasonically tested for internal flaws, and welded to the next one with automated submerged arc welding. The finished vessel gets heat-treated inside a furnace big enough to swallow it whole, X-rayed at every weld, then hydraulically pressure-tested. Decades of reactor operation ultimately depend on every one of those welds behaving exactly as designed. After all that, it ships by heavy-duty trailer and barge, because at that size, no other transport method exists. Not everything critical is a vessel. Plenty of it is rings, and rings need their own kind of forging line. Ring rolling takes a preformed donut of hot steel and squeezes it between an outer roll and an inner mandrel, while a manipulator rotates it through the mill. The ring gets thinner in cross-section and larger in diameter with each pass. On a heavy line rated for ingots up to 8 tons, axial profiling shapes the top and bottom faces during rolling. Machining a ring out of a solid block would toss 90% of the material in the scrap bin. Radial forging is the third method, and it's the one that makes long, precise shafts. 4 hammers arranged around the workpiece strike in perfect timing, while 2 manipulators feed the ingot through the center. On an 18 meganewton machine, the ingot can be up to 8 tons, finished diameter down to 130 millimeters, forging length up to 18 meters, all in one heat directly from the ingot. Up to 240 smoothing strokes per minute. Railway axles, high-speed train shafts, aerospace components, offshore pipe with wall thickness under 30 millimeters, all come off this kind of machine near net shape, which is another way of saying almost no leftover material. The shop's accountant sleeps well at night. Then there's the shape that's almost impossible to make any other way, the hemispherical dished end. Every pressure vessel needs a closure on each end, and for the highest pressure applications, that closure has to be a seamless hemisphere. This one starts as a flat circular plate, 125 millimeters thick and 2,100 millimeters inside diameter. The plate gets heated until it glows, dropped onto a 200-ton press that pushes it into a dished cavity in one stroke. In one stroke. That's it. Blink and the flat disc is a bowl. No welding, no seaming, no assembly. The whole hemispherical dome forms from a single pressing action. The reason it has to be one stroke is metallurgical. If the steel cools even slightly between passes, the grain structure ends up inconsistent across the dome. And inconsistent grain in a pressure vessel end cap is exactly what nobody wants when the vessel is holding 150 atmospheres of anything. That's why so few plants on Earth pull this off. The machine, the tooling, and the operators all have to show up at once, in the same room, with everything working. Miss one, and you're making a very expensive scrap disc. After forging, the part is roughly the right shape and completely the wrong dimension. A horizontal turning machine takes the forged shaft, mounts it between chucks, and starts peeling metal off the surface with a cutting tool while the whole piece rotates. Sparks, coolant, chips. The raw forging finally stops looking like a boulder and starts looking like a shaft. Turning gets close. The last few microns need grinding. A heavy roll grinder like this one holds a mill roll weighing many tons and spins it against an abrasive wheel until the surface is smooth enough to reflect light back at you. The tolerance on a rolling mill roll is measured in fractions of a hair. Nail the machining and the roll makes clean steel for years. Get it wrong and the whole line prints out garbage on a schedule. A serious forging shop has its own machining floor, and the numbers get wild fast. rings over 250 inches in diameter and up to 100 inches tall, shafts up to 80 inches across, 550 inches long, drilling operations up to 12 inches inside diameter, over 500 inches deep, all to hold tolerances tight enough that a forged shaft ends up smoother than most kitchen countertops. Which brings us to the floor-type mill, the machine that finishes the press head structures for other presses. With travel measured in tens of meters and a rotary traveling table strong enough to hold multi-hundred-ton workpieces, this class of machine handles the final boring and milling on press frames themselves. So after all this, the forging, the machining, the assembly, what does it actually take to keep this level of heavy industry alive? Everything you just saw runs on a relatively small number of forging plants worldwide capable of the largest work, and that concentration is starting to worry the engineers who watch the supply chain. Reactor vessels, wind turbine main shafts, aerospace landing gear, all trace back to the same handful of ultra-large presses. Some sit idle for months, then run flat out when an energy or defense contract lands. Building a new press of this class takes years and an enormous investment, so nobody adds capacity casually. Do you think the next generation of energy infrastructure gets held back because there aren't enough of these presses in the world? Or do smaller modular designs eventually make giant forgings less critical? Would love to read your take in the comments. Thanks for watching all the way through. Smash that subscribe button and stick around for the next deep look at heavy industry.